Hello, friends. In this series of learning computer organization and design, today's topic of discussion is bus transport. Let's understand the agenda of this particular chapter first of all. So, we have already covered the resistor transfer language and what is the meaning of the term resistor transfer in the previous sessions. So, today we are majorly focusing on the bus transfer, and if the time will allow, we will also discuss about the memory transfer. Then in the later part of these sessions, we will cover the micro operations. So as I discussed in the very first session of this disaster transfer and micro operation, that micro operations are playing a vital role when we are talking about the resistors and the data which is stored in the resistors. So for the time being, let's concentrate only on this particular topic, which is bus and memory transfer. Now, before beginning understanding about how we are connecting the resistors with the buses, let's understand that why there is a need to have a bus. Okay, so the very first thing is that if you look at this scenario in the digital systems, which is consisting of many resistors, it is impractical approach to have data and control lines to directly allow each resistor to be loaded in the with the contents of every other possible resistor. So let's try to understand this point first. What we have learned so far is that if there is a resistor, let's suppose R, who is having some bit, let's suppose it is this resistor is of 4 bits, and it wants to transfer the data to any another resistor. Let's suppose this is our resistor, R1 resistor want to transfer its data to R2. Then how I can perform that? I want another resistor R2. Okay, so what I will do, I this zeroth bit position will be changed with this 0. This will be copied at the first position, the second bit at the second level, and so on and so forth. So the idea is that this copying of the data from one resistor to another resistor, how it is taking place? It is taking place bit by bit. Means if the bit is present at the zeroth level, so definitely it should be copied to the resistor at the zeroth level only. So now think of a scenario within a digital machine. In a computer system or in a digital machine, what happens is that we are having thousands of the resistors available. Why so? Because these are the main resistors, which these are the resistors which are responsible for storing the data, right? So if I take a very simple example of, let's suppose, memory. So the data is stored in the form of resistors in the memory. Now in the memory only, there is not only the data present, the resistors are also responsible for storing the address of the data also. So you can understand and now try to relate the point that if for one resistor I can see that I need to design four different wirings. Okay, so think of a scenario when I will be one machine will be dealing with thousands of the resistors. So it would be impractical to actually attach each and every resistor or provide the wiring to each and every resistors like this. It will ultimately lead to the complexity, right? And along with that, it would be very much impossible to determine the fault also if it arises within the hardware. So for these two reasons only, we are relying on a new centralized architecture, okay, which we called as a bus system. So what happens in case of a bus system? The bus structure consists of a set of common lines. So this is the basic idea. So in the bus systems, we are working with some common set of lines, one for each bit of a resistor. Now, let's suppose we are talking about the bus system to be designed. So what I will do is, let's suppose it is a 2-bit resistor. There are so many 2 bits resistors attached. Let's suppose this is R1, R2, and R3. There could be n number of resistors. So what is the benefit of having a bus system with me? So let's suppose it has to transfer the data to this resistor number m. So what I will do, for one bit, like the bit which is present here, this zeroth bit, okay, so again for this zeroth bit and for this zeroth bit, or for those n resistors which are attached here, which are present here, I could be having a one common line to transfer the zeroth bit position to this particular resistor. Similar will be another common line for transferring the bit position 1. So ultimately what is happening here is I am trying to reduce the complexity by simplifying the structure. So this is what exactly is the idea of a common bus system. So this is what we called as a common bus. Bus is common for what? Common for the bits. Okay. So this is the point that we need to understand where it is common. It is common for each bit position of the resistor through which the binary information we are transferring to the another resistor. So how we are able to do this? We will be using some sort of control circuits to select that which particular resistor would have to transfer the data. Let's suppose now R2 has to transfer the data here on this M resistor. So there would be some sort of control functions or control signals or control circuits been there which will be handling this operation. Only R2 will be allowed to transfer its data on this common bus line, and R1 and R2 would not be able to do so. So we will be using some sort of architecture or some sort of constructing mechanism for that we will learn in the next slide. So this is how we are designing the bus systems. As I was explaining you earlier also, if I am having some number of resistors, so for each bit position, what I will be doing, I will be having some sort of bus lines available, right? So again, if I took the example here, this resistor A is there, if it is having these all are of 2 bits, A naught, A1, B naught, B1, then C1, C naught, D1, D naught, then what will happen? For transferring this bit position 0, I will be having one common line, okay? Same is the case for the first. I will be having the another common line. So wherever I want to transfer the data, mostly it would be transferred to the another resistor. Okay, so this is how I will be able to transfer the data on the common lines. So there are number of mechanisms which decides that which particular resistor actually has to transfer the data on through this common bus system. So the way there are basically two ways to construct the common bus system. One is the multiplexer and another is the tri-state buffer. So if you have to learn more about these, let's start understanding about the multiplexers. So how the multiplexers will help in construction of the bus systems? Because the multiplexers has a unique property. The property is that if it is having the availability of 4 or 5 or n number of, you could say that, different kind of informations, it will pick any one which most suits the requirement, and it will depict as an output. Means it is able to provide me some from selected output, okay, which is desirable or which is which has been needed, okay, from the available inputs. So how I am able to do so? So again, I am able to do so through the selection lines. So let's understand in more about how the selection lines are helping a source resistor to transfer its information over the bus. So in order to design a multiplexer or design a bus system using a multiplexer, there is a key term that we need to understand. The key term is that whenever I have to design a system using the multiplexers, I would always be provided with some scenario like here. So the question would be like, construct a bus system of 8 resistors which are consisting of 16 bits. Means I am having the availability of 8 resistors, so on up to 8, 1, 2, 3 to 8, and these resistors are of 16 bit each. Each resistor is having the capability. Now my point is that if I am saying I am constructing the resistors using the multiplexers, then I now need to remind that how many multiplexers are required for this case. Similarly, what could be the size of each multiplexer if I want that this particular kind of statement to be fulfilled or to design a bus system using the multiplexers. So how to do so? So the formula is very simple and straight. So if I am having k resistors, okay, and each consisting of n bits, so number of resistor multiplexers required would be n, which is equals to number of bits in the resistor, and size of each multiplexer would be equals to the number of resistors available. So for our case, like if I am having the 8 resistors available, each with capability of 16 bits, so it means that the number of multiplexers required are 16 for this particular arrangement, and the size of each multiplexer would be 8 cross 1. So this is what has been depicted here. So if the multiplexer has this size, so definitely I need 3 selection lines for it, as simple as it is. So let's learn this in more detail by simplifying the example. So this is one of the example. The example says that we need to construct a bus system of 4 resistors. So what we need to have is we need to have work with the 4 resistors. So another thing is that each resistor is consisting of 4 bits. Means each resistor has the capability to store 4 bit of the information. So what I need to do is, first thing is that I need to remember what are the number of mux is required and what is the size of each mux. So the number of multiplexers required would definitely be 4, okay, because number of bits are 4, and the size of each multiplexer would be 4 cross 1. So for this, I knew that only 2 selection lines would be required. So for that thing, this is the selection lines, this is the function table. It says that if the selection line is 0, 0, always resistor A will be selected. If the selection line is 0, 1, resistor number B will be selected. Similarly, C and D will be selected for the other combinations. So let's understand it in more detail, that how it will be able to provide me a common bus line with the use of this entire scenario. So what I did is I have designed a layout here. So let's understand how I can design the circuit diagram for this. So these all are the resistors, and these are the multiplexers. Let's suppose this is mux number 1, this is multiplexer number 2, multiplexer number 3, and multiplexer number 4. What I did is, these are the 2 selection lines. Definitely these would be commonly attached with all the multiplexers which are available. And what I need to remember is that what is the input been coming in these multiplexers. So that is the point to understand here. So what I am saying these all are the common lines, the output which has been generated from these multiplexers. Okay, so it means that if there is a resistor which is consisting of 4 bit of information, so definitely I will be having a destination resistor which is also of size 4 bits. So for transferring the first, the least significant bit in this at the 0th position, what I will do is, in this multiplexer I will only have the least significant bits of the number of resistors which are available. So let's provide that. So this A naught will go here. Okay. Similarly, this B naught will be attached here. Similarly, the C naught will attach, and the lastly, the D naught will attach to this first multiplexer. So idea is that each multiplexer will contain the 1 bit position of all the resistors. So this is the point that we need to understand. If this is the least significant, I can say this is consisting of the most significant bit. So here also, so what I need to do is, for my simplicity only, I need not to design each and everything, not to design the wiring, because it will lead the complexity. This is how I can start designing the system. The only thing that I need to depict is that what is the input been coming to these multiplexers. So here, as the 0th position is covered here, so definitely A1, B1, C1 and D1 will be provided in this multiplexer number 2. Similarly, A2, B2, C2 and D2 will be provided here. And the last one is again the similar case, A3, B3, C3 and D3. So ultimately, how this entire circuit will work. So as I discussed with you earlier also, the selection line will be responsible for transferring the data. So let's suppose for this selection line 00, A will be able to proceed with the transferation of the data. Similarly, B, C and D for the other available selection inputs. So how this data transfer will take place? Let's understand that in more detail. So let's suppose the data in the selection line is this 1 and 0. So all the multiplexer will receive the same information in the selection lines. So what will happen? So as I always say, always consider that these 00 in decimal is zeroth. These are representing the zeroth pin of each multiplexer. Similarly, this 01 representing the first pin, 1 2 second, and this is the third pin, right? So as the selection lines are 10 in decimal, it means the second line. So I know that the input from the second pin means this pin of the multiplexer will be selected. So what is actually present here? So here it is C3 present, C2, C1 and C0. So ultimately here in the destination register, this is what I am getting. This diagram is very simple if you can understand. So this is, I think, the best method to understand that how this entire common bus system will be designed. So now I believe that if you are provided with any kind of question related to the bus design using multiplexers, you can easily do it. So idea is very clearly depicted here. Even if you have any doubt, you can ask the doubt. So moving ahead, now is the next point when we have to construct the data using the three-state buffer. So let's understand the meaning of three-state gates first. Three-state gates are like normally when we talk about the gates, being it any logical gate, right? So that it is having two kind of states. One is the input state and one is the output state, right? Only two states are available. We provide some input variables. It could be one input data also, it could be two inputs also. So one two जितनी भी inputs मुझे provide करनी है, but the output will depend upon the input and output will always be generated as a one. So these are the basically two states kind of gates. Normally the logic gates consist in this. But if I will provide a third state also, third state will actually be nothing but the controller of this input flow towards the output. Okay, so this is what is the meaning of the term three state gates. So let's understand in more detail. A three state gate is a digital circuit that exhibit three states in which two of the states are the signal equivalent to logic 0 and logic 1 only, as in the conventional gates. The third state is nothing but the high impedance state, which will restrict the excess of the flow of input towards the output. Okay, so high impedance state behaves like an open circuit, which means that the output is disconnected. You remember whenever in the physics we used to design the circuits, there was always a key, and if this key is open, it means the circuit is not complete until or unless this key is actually closed. So if it is an open circuit, it means it is in the high impedance state. So this is the meaning of the term. So what we are going to do here is, our basic agenda is that we are going to learn the three-state bus buffer. Okay. So this is the symbolic notation. I would like to explain you entirely through here only. So normally this is how the buffers work. Buffer is having two states normally, in input state and the output state. And we know that in the buffers what happen is that whatsoever the input is coming, the same output will be delivered ahead. But what we are doing in this case of three state buffer is that we are using a third input, which is the control input with the name C. So what this C is doing, the entire flow of this input towards the output is now dependent on this control input. If the value of C is equals to 1, means if the circuit is closed, if I say the key is actually closed, so only in that case the a this input A will be transferred here as an output. Otherwise, if this circuit is having the value 0, it will be depicted that it is in a high impedance state, or it could be a open kind of circuit. So this is what the point is. So we will learn now that how the application of working with this three state buffer can help me in the design of a bus system. So let's understand that. So here I have considered one example. The example is that now I am using the scenario where I am having four resistors present. Resistor number A, resistor number B, resistor number C, and resistor number D. Okay, let's suppose these all are the four resistors available, and each resistor is consisting of one bit only. So how I can design this entire structure using a three-state buffer? So idea of the bus system will remain same, that on the common line, the line will be common for the one bit position only. Okay. So the idea here is that if this is a bit position and this is, let's suppose, a resistor with the name M. So what will happen in this case is that I will be using a 2 to 4 line decoder. Reason being, here I am having the number of resistors equals to 4. So how this will help me? These are the two input lines. We know that in case of decoder, how do the decoders work? For 0 0, either D naught will be active. For 0 1, D1 will be active, or the first value will be active. For 1 0, the second value will be active. For 1 1, third value will be active, right? So there is one enable. We know it is just acting as a whether the circuit is connected or not. So if enable is equals to 1 and having certain value here, okay, so this particular value is actually going to decide now that whether the A resistor is going to transfer its data, B, C, or D, which one is going to transfer its data. So let's suppose the value of this selection line is 0 1. So I am saying in case of 0 1, the B should have the authority to transfer the data. So 0 1 simply means the one number. So means this pin is active, rest all are 0 0. So if these are 0 0, it means these all are in high impedance state. These would not be able to transfer the data. Only this particular resistor with the value B naught can take its data on this common line and can proceed here. Similarly, depending upon the values present in the decoder, I would be able to depict the results. I hope that you have understood this idea of constructing the three-state buffers and constructing the three-state buffers or the bus system using these buffers. So this is the very last topic today, which depicts that the memory transfer, how the transfer is taking place between the memory. So for this point, at this point of time, we need to understand only that there are only two operations being done on the memory. So memory में क्या किया जाता है? Either I can perform the read operation, I can read the data which is stored in the memory, or I can perform the write operation. I can update any data which is available within the memory. So how this read will perform? So in order to read any data, if you know about the things how the data is stored in the memory, always there is some address present. Okay, like if I have to reach any particular home, then I need to know the house number. So these addresses are nothing but the house numbers. So I need to refer to the address register of the memory, so where the data is placed. So let's suppose this is the address 100, and on that particular address only I can have that particular data available. That data I will place in the data register if I have to read the data. Or if I have to write the data, how I can write it? Any register R which is having some value present, it will transfer its data to the any particular address value of the memory so that it can write the data here in the memory of the address register. So these are the only two simple points to understand. I hope that you have understood the today's session. Thank you so much for joining the session.